Now that we have finished our unit on gases, this is just a really brief lecture on a couple of random concepts related to gases. Specifically, we're going to focus on vaporization. And just a quick reminder first that it is the strength of the intermolecular forces, those attractive forces between molecules, that determine the phase of matter that something's in, whether it's a solid, liquid, or a gas. And the primary intermolecular forces that we went over last semester, the weakest and the type that all atoms and molecules have are London dispersion. When that involves a molecule, it means the molecule is nonpolar. And then if we have polar bonds and asymmetry, we will have dipole intermolecular forces, which are stronger. And particular, got that wrong. London dispersion forces are temporary temporary induced dipoles. So dipole for polar bonds, polar molecules. Hydrogen bonding is a specific type of dipole attraction that is particularly strong and occurs only when a hydrogen atom is directly bonded to either fluorine, oxygen, or nitrogen. Three very electronegative, quite relatively small anions. Non-metals. Alrighty, and then we talked briefly about ion dipole. Those are intermolecular, but that is what we see in solutions. When we dissolve an ionic compound, for example, in water, and the first thing that happens, so let's say if it's sodium chloride, the first thing that happens when that dissolves in water is it separates into the individual cations and anions, and then these individual ions are solvated by water molecules. And so this solvation, this attraction between the ions and the water molecules are called ion dipole, and they are stronger even than hydrogen bonding. All right, so phase diagram, you may have seen one of these before, but it plots temperature versus pressure and tells us what combination of temperature and pressures we are going to have, either solid, liquid, or gas. Now, we are used to changing the phase of matter simply by heating, right? Because our atmospheric pressure is 1 atmosphere. Let's just assume it's there. I don't even remember what this particular phase diagram, what substance it's for, but let's just assume we're at 1 atmosphere. Well, if we're at 1 atmosphere, unless we create a vacuum or induce artificial pressure, everything we do is going to be along this line. All right, so if we raise temperature, we're still going to be at the same pressure each time. Okay, but it turns out there's a whole nother world out there, right? So if you change pressure at all, let's say we introduce a partial vacuum and we get to 0.5 atmospheres, then we start heating. Okay, we're going to have a totally different type of behavior. Same thing with higher atmospheres. But to go back to the phase diagram, it's always arranged like this, with solid to the left, okay, right, makes sense at the lowest temperatures, liquid in the middle, and gas at the higher temperatures. I call it the slug diagram. And the lines on the diagram itself, so here, here, and here, represent, so the line in between solid and liquid is, we're going to call it melting line instead of melting point, because the melting point that we refer to for something is right here, again at 1 atmosphere pressure. But if we change the pressure even a bit, the melting point is also going to change. And the line to the right in between liquid and gas, we will call this the boiling line. And again, the boiling point, the normal boiling point that we deal with is at 1 atmosphere. right? Okay, and then down here, that's between solid and gas, so we could call that the sublimation line. All right, so obviously, as you change pressure or temperature, the other variable is going to have different values depending on what the temperature and or pressure are. And actually, I'm going to give this example here just because it's kind of cool. And it helps you remember how to use the graph. Okay, so this is water. I see that now because at our normal atmospheric pressure of 1 atmosphere, the boiling point of water we know is 100 degrees Celsius, right? However, what if we're at a higher temperature? So, and this is how pressure cookers work. They don't go as high as 10 atmosphere, but just to make my point, I'm going to argue. Let's say we were in a pressure cooker and the atmosphere that was 10 atmospheres. What temperature then would water boil at? Well, instead of 100 degrees, water would boil at 200 degrees. So what is the rate at which your food will cook if water's what you're cooking your food in? Your food is going to cook much faster, right? Because it's going to be maintained at 200 degrees. So remember that when something boils, it doesn't get any hotter, right? So when water starts boiling, it stays at 100 degrees until all the liquid's boiled off. So that is your cooking temperature at normal 1 atmosphere. Now, you have probably seen some recipes also that say, like, if you're making a recipe at a high elevation like Denver or something, that's going to be lower atmospheric pressure. So now let's go the other way. Let's say that we were at and that's way too low, but just to make the point, let's say we were at a pressure of 0.1, 10 times less than normal. What would the boiling point of water, when would water boil? It would boil at 50 degrees, right? So if you were some things would never cook at 50 degrees, right? So, but anyway, food would take longer to cook if you're using water as your the base to cook it in. Anytime you see the language of standard or normal boiling point or melting point, that is telling you that that's at 1 atmosphere. So remember that. Here's the typical type of graph interpretation question you might be expected to do. So read this, and it says, describe the phase changes that take place when the pressure, let's see, at a temperature of minus 25, so looks like we're about here, and at that point increase the pressure from 0.001, which is right at the bottom of the graph, and increase the pressure up to 100 atmospheres. So we're just going to do this. So now what has happened? They want us to describe the phase changes. Well, we started down here and we were a gas, right? We were in this orange phase. And then we crossed, what is this that we just crossed? That is going from the gas phase to the solid phase. Not sure if you know what that's called, but that is called deposition. It's the opposite of sublimation. Deposition, and then we stayed in the solid phase after that. We did not undergo, kind of tilted to the left here, but we did not undergo another phase change. So that answers part 1. Oops, meant to put the eraser on there. There we go. So the second part of the question is going to hold pressure constant and change temperature. All right. So this time we'll keep it at a pressure of 100. So that's right here. And we will vary the temperature from minus 25, so I'm eyeballing it, being kind of sloppy. Okay, all the way to 350. Okay, so about here. All right, so how would you describe that change? Well, we started at a solid, then what did we do? This is the line between solid and liquid, so then we melted it. Okay, so at any melting or boiling point, you have an equilibrium. You have two phases present. So this would be at the line, a mixture of solid and liquid. And then we had another phase change over here. So then we boiled or vaporized. And when we were on that line, we had a mixture of liquid and gas. And we ended up in the gas phase right here. Right? So pretty easy. And this page is just saying the same thing I went over in a little bit more formal, neater form. All right, a few more slides. I'm going to talk a bit more about intermolecular forces and specifically phase change from liquid to gases. So speaking of going from a liquid to a gas, we either call that vaporizing, right, or boiling. Boiling infers that you are making the vaporization happen, that you're adding heat. That's kind of how we've come to accept that. So as I said, the strength of the intermolecular forces, of course, affects state of matter. It also affects solubility. Because remember, the molecules or atoms are strongly attracted to each other, so before they're going to interact with any other substance, such as they would have to when dissolving, the intermolecular forces with this new substance need to be even stronger. Because it determines the state of matter, it also determines the boiling and melting point, as well as some other properties. So speaking of boiling or vaporizing, if you have very strong intermolecular forces, that means that it does not want to boil. And I'll show you diagrams of that. But if you have something like water has hydrogen bonds, right? So you have these water molecules that hold each other very close together. Okay? And so because these are strong, it's going to take more energy to disrupt them or loosen them, which is what needs to happen for the water molecules to move into the vapor phase. We're going to talk about vapor pressure and a new term for you called volatility. So you can come back to this one. So here's kind of a straightforward question that would want you to use intermolecular forces to explain differences in boiling points or melting points. Same thing. We just happen to be talking about gases. So let's say you were comparing this compound, which is called dimethyl ether, to this compound, which is called ethanol. They have the same molar mass, but their boiling points are significantly different. Okay, the ethanol boils much higher. And what does that mean? That means that the intermolecular forces of ethanol are stronger than the intermolecular forces of ether, diethyl ether. Okay, why? So anytime, just make a note of this, anytime you are explaining melting point, boiling point, state of matter, you want to identify the type of intermolecular force. Now, if you need to refresh on intermolecular forces, I have plenty of pre-recorded lectures on my YouTube channel on that, if you need to kind of give yourself a brush up. So how you go about, you want to identify the strongest intermolecular force in either of these. So this is what you ask yourself. Does the molecule have a polar bond? Because that's one of the requirements for a polar molecule and either dipole-dipole or hydrogen bonding. And then you want to make sure that it is not symmetric in order to be dipole-dipole or polar. All right, so in order to do that, you need to draw Lewis structures, right? So if you just looked at ethanol, I didn't mean to erase that, if you just looked at ethanol, you might think, well, that's linear and it's symmetric, right? So maybe it's not polar. No, okay? So if you drew a Lewis structure, which you need to do, you'd realize there were two lone pairs on ether, just like there are in pretty much every molecule that has an oxygen atom, neutral, is going to have two lone pairs on that oxygen. So going back to the old days when we did Lewis dot structures, it says 4 domains, 1, 2, 3, 4. So it starts with a tetrahedral molecular, electron domain shape, and the molecular shape is bent. Okay, so just looking at the atoms themselves is bent. So this is not symmetric, and that's one of the requirements for being polar. So this is definitely polar, which means it has dipole-dipole. Dipole-dipole is the strongest IMF, intermolecular attraction, that this dimethyl ether has. It can't hydrogen bond because in order to hydrogen bond, the hydrogens have to be directly attached to oxygen, fluorine, or nitrogen, and they're not. They're attached to a carbon. Anyway, so we have dipole-dipole. Now, remember the ethanol, we're going to do the same thing with ethanol. Ethanol has a higher boiling point, which means its intermolecular attraction is stronger than ether has. So it's got to be hydrogen bonding, right? Because this one's dipole-dipole. And if you look at it, yes, it is, right? So you have a hydrogen directly attached to an oxygen. That's always hydrogen bonding. So this guy, ethanol, has the stronger or higher intermolecular force, and that's why it takes more energy to boil it. And again, this is all just kind of explaining what I just did verbally on the last slide, but it is there for you. All right, so let's talk about vapor pressure. Any liquid at all. So you've probably noticed if you have a glass of water around with just little remnants of liquid in the bottom, and you let it sit, it's going to evaporate, right? So any liquid, is the surface molecules are going to, some of them, escape into the air. And so slowly over time, that liquid's going to evaporate. So what is vapor pressure? Vapor pressure is the pressure exerted by the gas that forms over a liquid. Okay, let me say that again. Vapor pressure is the pressure exerted by the gas molecules that have formed over a liquid. So the more gas molecules or atoms, whatever the gas is, you have over a liquid, the higher the vapor pressure is. So, and the definition of boiling point, you may remember this, is when the pressure exerted by these molecules that have escaped from the surface of the liquid, when the pressure they exert equals atmospheric pressure, that is defined as the boiling point. So imagine you have a pan of water on the stove, right? Okay, we're going to pretend like you can see through it. And so even at room temperature, you're going to have some of the water molecules that are going to escape into the air, okay? So here's going to be your vapor pressure. Now, if you turn the heater on below that pan of water, it's supposed to be fire, it's going to start warming up. What's going to happen to the vapor pressure when you warm a liquid up? You're going to get more and more and more molecules, right, that have escaped into the gas phase. Okay, so you're going to have higher vapor pressure. And so that tells us, and that should have been intuitive anyway, that as temperature goes up, vapor pressure goes up. Now, they're not a linear relationship, but as one goes up, the other goes up for sure. And you can think of these molecules that are in the vapor phase exerting pressure kind of up and away from itself. And then you can also imagine atmospheric pressure kind of pushing down. Okay, so when those two pressures become equal, that is the boiling point of that substance. and you have a mix of liquid and gas together. Now, the new vocabulary word, there are some things, and you know this also, that are much more prone. They'll release many more molecules from the liquid into the gas phase over them. They'll much more readily do that. We call those materials volatile. So you may have heard volatile organic compounds. It's one of the safety things that a lot of items manufactured have to report. So let's imagine you have a container with rubbing alcohol, which happens to be isopropyl alcohol. So there are 3 carbons, 1, 2, 3, 4, 5, 6, OH. 1, 2, 3, 4, 5, 6, yeah. And let's say you have another one of water, and then a third container with cooking oil, okay? Which one do you think is more volatile? And you should know each of these 3 just from your life experience. The rubbing alcohol is going to evaporate faster, right? So that tells us that the vapor pressure of rubbing alcohol is higher at any temperature, right? Yep. Vapor pressure is higher. And then, which means if vapor pressure is higher, there are more molecules in the gas phase, right? So, and then H2O is, it still vaporizes, but not as much. The vapor pressure, there aren't going to be as many of the H2 molecules in the air above it. So the vapor pressure is going to be lower. And oil is not very volatile at all. That's going to be very low vapor pressure. So you could spill oil on the counter and leave it for days and it would probably still be there. So it does not vaporize very much. Now, what is determining the vapor pressure of these 3? I could also ask the question a different way. What explains the difference in boiling point? So anytime you're asked to explain difference in melting point, difference in boiling point, difference in vapor pressure, it's all intermolecular forces, okay? So you would just, the one that has the higher vapor pressure, okay, remember high vapor pressure means more molecules in the gas phase that have escaped from the liquid, okay? So what does that say about the intermolecular forces? If you have more molecules in the gas phase, if you have a higher vapor pressure, the IMF are lower. Another type of curve for you to interpret, yay. I did mention before that as as temperature goes up, then vapor pressure also goes up. It's not a linear relationship. You can see these are not lines, but as one goes up, the other goes up. Okay, so see that temperature is on the x-axis, vapor pressure is on the y-axis. Now, why do they have individual curves? So what can we say? We can say that this substance, this is ethylene glycol, this is antifreeze. We can say that that one takes more energy to vaporize, right? Because you have to get to a higher temperature before it starts increasing the vapor pressure. It takes more energy to vaporize. And that the one down here takes less energy to vaporize. Now why? Any of these things that are talking about the temperature at which something changes phases, it's intermolecular forces. So you can see ethylene glycol, it's got hydrogen bonding capability on both ends. So very, very strong intermolecular forces. And then the ether on the other end, that's just like the other ether we looked at, that it has dipole-dipole. All right, and then the ones in between. It turns out, like I said, it's not linear. has a logarithmic inverse type of relationship, kind of convoluted. But it turns out that if you have, let's see, if you have one set of data for vapor pressure, see the P's here stand for vapor pressure. If you have one set of data for vapor pressure versus temperature, and then you want to know what the pressure would be if you change the temperature, you can use this equation. This is called the Clausius-Clapeyron Equation. It's a little convoluted to use. It's similar when we were using the Bohr model and the Rydberg equation, right? So we had the Rydberg constant and then went over, right? That famous equation I got wrong, or I wrote wrong on the first exam. So because of this, and this gets confusing, I want to point out the different versions are of the Clausius-Clapeyron equation. Now look at these two. They look very similar, but they're different. Okay, one of them has a minus sign in front of the whole thing, the other does not. The first one with the minus sign, T1 comes first, and in the second one without the minus sign, T2. Now these are equivalent. Okay, they will both solve any of your equations. Okay, so one isn't wrong and right, they're different. And so different sources use different ones for different reasons. So, anyway, I just didn't want you to get it thrown if you see the different versions. All right, so this can be a little tricky to use and isolate. So I'm going to walk you through an example. All right, so here is an example. All right, so here's the compound and normal boiling point. Remember I said anytime something says normal or standard, that means at atmospheric pressure, okay? So the normal boiling point is 99 degrees. And if you remember that equation, I can show it to you again, but you have to know the enthalpy of vaporization. That's a constant will be given to you. All right. And so it's saying what is the vapor pressure at 25 degrees? So what have we done? We have lowered the temperature. So let's just think through this. What do you expect to happen to vapor pressure at a lower temperature? As you lower temperature, you expect vapor pressure to also go down, right? So let's go ahead and plug in and pay attention to how I simplify it because it's a little tricky. That's just the question stated again. A couple things I wanted to point out first, things that can kind of throw you off on this type of problem. All right, check units, as you should for every problem, especially in gas laws. I think because the gas law calculations are not that hard, I think they try to put extra challenge in by messing with units. So just kind of a reminder, as with any gas law, temperatures must be in Kelvin. So I went ahead and converted the temperatures given here to Kelvin. All right, now something you may not have noticed is that the enthalpy of vaporization was given in units of kilojoules. And the value of R, the gas constant that we're going to use, and I'll show you that value in a minute, is in joules. All right, so just be careful of that kind of thing. So I'm going to go ahead and convert the enthalpy of vaporization from kilojoules to joules right now, okay? All right, so now let's look at the formula again, and let's plug in the values we know. So the original vapor pressure, now it doesn't matter the units of pressure as long as both of the values match, okay? Because look, it's a ratio, so units are going to cancel. All right, so we can just keep the torr that was given to us. Well, it said standard pressure. So standard pressure is either 1 atmosphere or 760 torr. But since they asked us to give the answer in torr, let's just put them in torr now. It makes it easy. So here's standard temperature. That's the original one, P1, right? And we are solving for P2. Then enthalpy of vaporization was given to us. Remember, we changed the units to joules. The R value you're going to use for this one, now pay close attention. This is a different R value. You are used to using R value that has units liters, atmosphere, mole, Kelvin, right? This one is going to be joules. So just pay attention to R value. The units of R have to cancel out all over the place with the other things. Temperature is always Kelvin. So what do we get then? When we simplify that, we get that, I'm just going to rewrite it here. So now we have that log of P, we'll just call it P2, the second pressure, over 760 equals, and all of this math, you can verify it simplifies to minus 2.826. Now, in case you're rusty on this math, if you want to get rid of a natural log, ln, you raise the whole thing to e. So we're going to do e and then raise everything after that, log of P2 over 760. Now anytime you have e and then raise to the ln, those cancel each other. So that simplifies to simply the second pressure divided by 760. Got to do the same thing to both sides. Okay, you got to e to this side and then e to this side. So all of that equals e to the minus 2.826. So now you need to put this in your calculator, make sure you're entering it correctly. E raised to the minus 2.826. All right, so I'm going to go ahead and tell you what I get so you can make sure you're using your calculator right. So when I find your e to the e button and e to the minus 2.826, you should get 0.05925. Carry some extra digits. And so now we have P2 over 760 equals that. So now to simplify, all we need to do is multiply both sides by 760, right? So that we get P2 by itself. And so when you do that, okay, you get 45. 45 torr is the second pressure value. Let's see if that makes sense. Let's go back to the question. We were at a higher temperature originally, and the vapor pressure at that point was just normal atmospheric pressure. Because remember, boiling point means vapor pressure equals atmospheric pressure. There, that's why they're equal, because we're at the boiling point. So atmospheric pressure was 760 torr at 99 degrees, and we took it down to 25 degrees. So the vapor pressure should go way down, and it did. It went from 760 down to 45. So it seems to be good. And that is it for this kind of random lecture on vapor pressure, intermolecular forces.